let's go ahead and get started. We some information for you guys if you haven't been paying attention to your Canvas site. As you know, we're going to finish up section 6.5 today and then start section 6.6, which means we're getting pretty much to the end of the road of chapter 6, which means test 2 is coming around the corner. Now we're really heading right on schedule with our terms of tests and stuff, with our course calendar and things. So if you pay attention to your Canvas site, you will notice that I actually posted some stuff already for you guys down here. And there are two things that I happen to post for you. There is your first calculator project, which is based upon the material that we're actually doing today and last class, and which is due on Wednesday, the February 15th. And then there is the traditional test review homework, which I'm calling homework number 3 because I like to keep these things in order. Homework number 3, which is your test 2 review, which is due on Friday at our review session, February 17th. All right? So, which means what? When is your next test going to be? Test 2. Monday, February the 20th. A week from Monday. So you've already know the date, you know the time and everything like that. Now here's what you don't know. Now, we started chapter 2, so we got section, 6.3, test 2 material, 6.3, 6.4, 6.5, 6.6, because 6.1 was on the first test material, but that doesn't matter. What I'm doing to you guys in terms of test number 2 is I'm going to give you guys a general integral test, which is going to be stuff from chapter 5, basic rules, U substitution, integration by parts stuff that you still need to know, as well as the partial fractions, the integral tables, the linear approximation, and the new stuff, which we will get started on today, which is the improper integral stuff. So it's going to be a complete chapter 5 and chapter 6 test. Let me explain why I'm doing this. After we finish with chapter 6, my focus is going to change. Right now, my focus is making sure you guys have the intellect and the ability to integrate antiderivatives and use that stuff. When I get to chapter 7 is about applications. What can we actually do with these integrals? Basically, in a nutshell, we're going to be doing physics word problems. So my focus is going to change from integrate, to set up the integral to do some type of calculation. So we're going to be doing some kind of major word problem type thing. We have to set up an integral that does whatever we needed to do in a certain physical relationship here. So again, my focus is going to change. So I'm going to hit you hard on test number 2 in terms of the ability to pretty much integrate everything. So for those folks that didn't do well on your home test number 1, here's a great time to redeem yourself, because this will really let me know that you guys know what you're doing and you're worthy of moving on to the physics application stuff. Also, for those folks that did do well on test number 1, don't get cocky. You could get burnt by test number 2. Go back and practice this stuff so you make sure you do well on test number 2 as well. Because again, my focus is going to change when it comes to the chapter 7 material, which is, like I said, physics applications and stuff. All right, so also to let you guys know about your website here, your calculator project has been listed under your the assignments tab. So if you come over here to assignments, you will see, and you get to see more stuff here because I'm in charge of the class thing here. Here are all your pre-section quizzes, and great. But here it is. Here's your homework number 1 with your test review 1, which you've already done. Here's your calculator project number 1. And here's also the assignment for homework number 3, test review 2. We'll go to the homework number 2 calculator project. If you click on that, you will notice that what you get to see. You see there are actually 2 links here. Those 2 links are for a TI-8384 calculator and for a TI-89 calculator. For you see, the operating systems on the 8384 is different than the 89. So I had to come up with another program and basically rewrite my program for the 89 because of the different operating system. This is a program that gets your calculator to do the Riemann sum stuff for you. The midpoint, the trapezoid, the Simpsons, the left and the right. It does it all for you. So which means that when we do these particular problems on a test, it's not just about getting the right answer, because I can show you how to use your calculator to get the right answer. It is about writing up the formulas, knowing how to plug the numbers into the formulas. This calculator is really designed to help you, because where most people will mess this stuff up is very simple. They'll put a parenthesis in the wrong spot when they're doing e to the x squared or something like that and trying to sum up 15 times. And one little parenthesis in the wrong spot messes up the whole problem. So it's designed to help you make sure you did the calculation correctly. But the real focus is going to be making sure you guys actually write the forms and stuff. So we'll do some problems today to actually talk about this. But there, like I said, are two projects. And I'll show you what this program does for you. So let's click on this one right here, this project. Here's what the project is. Now, it talks first about project number one. It talks about the left, right, Riemann, Simpsons Rule, gives you some ideas. And we still talk about the idea that the trapezoid, the Simpsons Rule, is actually equal to 1/3 the trap plus 2/3 the midpoint rule. And this is the kind of stuff we're going to be talking about today, which is the error-bound stuff. But here is the program that allows you to actually get the calculator to do left, right, midpoint, trapezoid, and Simpsons Rule Riemann sum. Now, there's two ways that we will allow you guys to do this. Now, for my computer science and computer engineers in here, you guys should be really excited about this fact, because you're going to learn how to program on your calculator. And then basically we teach you guys where the program buttons are located at. And basically your goal is to enter this stuff into your calculator as a program and figure out all the nuances. You can do that. There's another way you can get this program on your calculator. If you happen to have a friend that's a computer science major that went ahead and typed this thing on the calculator, there's a link cable that you can link these calculators together and transfer from one calculator to another, and you can cut, copy, paste your program to somebody else. Now make sure your program works first, because it's awfully wrong to send somebody a wrong program, and then they're going to be as low grade as yours. So make sure the thing works. So like I said, either way you guys do it, but we're trying to get you guys into the science and technology behind this stuff. So here's the program. Now, from that, once you get the program into your calculator, the first thing we do is we actually give you the information about one of the functions. So when you do, you can check the program and make sure the program is actually working, because it should spit out these particular numbers. If it doesn't, well, then your program's broken. You screwed up something or other. You got to go back and fix it. Now, once you got the program working, we're going to be asking you guys lots of questions about it. But again, it's a calculator project, so you'll be typing a bunch of functions in on the calculator and asking you to do, n equals 10, 20, 40, and 80. And you want to find the Riemann sums of left, right, trapezoid, midpoint, and Simpsons Rule. And then we're going to ask you which one's the best approximation, what's the good values here, what are the error bounds going to be, and stuff like that. And we'll talk about that today. And we give you a few problems to understand the power of the Riemann sum stuff, and also the power of the calculator and what it's actually doing for you. This project is due when? It's due Wednesday. And again, I put two of them up here, because depending on what kind of calculator you happen to have. And that being said, when I go back to assignments over here, you also notice that your homework number 3 is going to be due that Friday, because test is on Monday. So just to let you guys know, and I'll go back to the dashboard home thing here. In case you missed it, it's right here on your front page of your home thing. I got the little note. Homework number 2. Homework number 3, which is your test review 2, and then test is going to be on February the 20th. So there you go. All right, let's continue on. Last time, we were working on left, right, midpoint, trapezoid, Simpsons Rule, Riemann sums. Now clearly left, right, midpoint were things we did from chapter 5.1, but we're going full circle. We're now gotten such nasty integrals that we can't integrate them. Not because our calculus skills are not where they need to be, it's because you don't have an integrable function. what am I going to do if my life depends on me finding a solution to this, integrating this function, but this thing doesn't have an antiderivative to it? Well, as long as it's got bounds, you can at least approximate it. And so we have the midpoint, trapezoid, and Simpsons rule. And these are the problems we did last time, so I just thought I'd throw them up here. We did an e to the x squared from 0 to 1 using the midpoint. We used the integral from 0 to 1 of e to the x squared dx using the trapezoidal rule. And then we actually talked about, we did the integral from 0 to 1 of e to the x squared with 6 partitions using Simpsons rule. And so we wrote down all the little formulas for you guys, and this is where we want to pick up today. Now, if you turn your page over, the next thing after you learn how the process of how the midpoint, trapezoidal, and Simpsons rule works is this, something called error bounds. Error. Now, we have something called the actual error. To calculate the actual error of a problem that you've done, the Simpsons rule or trapezoid or midpoint or whatever Riemann sum you did, the formula is this. It's actually the true integral from a to b of f of x to the x. So you get the actual integral answer, and then you subtract off the approximation. This is how you get the actual error. You take the true integral and subtract off the approximate. And then and that tells you how much off, quote unquote, your answer from the approximation is. Okay? But there are formulas for trying to get what we call error bounds on these guys. If you were using the midpoint rule, there's a mathematical formula for bounding the error on the midpoint rule, which is we call E sub m, E for error, subscript m for midpoint. It's less than or equal to k times b minus a cubed over 24n squared, where this weird k, that k number out front, is actually equal to the second derivative absolute value less or equal to k, for a is less or equal to x, less or equal to b. Well, that's the mathematical formula. Let me give it to you in English. K is the maximum value of the second derivative over your interval. You got some kind of bounds on the interval from a to b, so you only look between a and b. You don't care what's happening over there at 102 if it's not within a and b. You look between a and b, you take the second derivative of the integral of the function you're trying to integrate, and then you look to see what is the maximum value or the farthest distance away from the x-axis that particular function is. And that value is going to be k. That is for the midpoint rule. For the trapezoidal rule, the formula is k times b minus a to the third power divided by 12n squared, where k is the maximum value of the second derivative, once again, between a and b. What is the difference between the error-bound formulas for the midpoint rule and the error-bound formulas for the trapezoidal rule? One big difference. What is it? You're dividing by 24 with the midpoint versus dividing by 12 with the trapezoidal rule. That's it. It's the same formula. But here's the deal. Which one is quote-unquote better? You notice with the midpoint, you got a larger number in the denominator, 24, versus the trapezoidal rule, you got 12. So when it comes to fractions, the bigger the denominator, the smaller the overall fraction is. Does that make sense? So this actually gives you a smaller error than this guy does by a factor of 2, if you think about it. So the midpoint rule is quote-unquote better than the trapezoidal rule in terms of approximating this stuff. And then, it gets worse though. The Simpsons rule. Simpsons rule error, ES, is less than or equal to k times b minus a to the fifth divided by 180 into the fourth, where k is the maximum value of the fourth derivative over your interval between a and b. Okay? Now, this is calculus class. What does that mean? Memorize everything. We don't give you formulas. We expect you guys to look at it, go, interesting, have it memorized, and move on and have that instant recall. Now, when they've done the problems in the past on the final exam, I'll admit this to you, usually they remind you of what the formula is. Usually, but not always. So that one time in the last 3 years that they didn't give them the formulas, well, it's about time for them to start doing that again. So make sure you have these formulas memorized, because on my test, I'm not going to give you these formulas, because I know you're going to need these formulas in the final exam. Therefore, go ahead and put it with the other 100,000 formulas you've got to memorize for this class. It's calculus too. Doesn't get better than this. All right, so here we go. Let's do a particular problem. Now, we've already done part of this. This is continuing on what we did last time. So, for the function e to the x squared, find the integral from 0 to 1 of e to the x squared dx. Now, what I meant by this was use your calculator. The reality is you can't integrate e to the x squared, so finding the actual integral is actually impossible. But there's a program that's being used on your calculator. Let's go ahead and see what the calculator is going to give us for that. And we'll just assume that as being the right answer. So, here we go. I'm going to go math number 9. I'm using my famous T84, and I got the upgraded operating system on this thing. Integral from 0 to 1 of e to the x squared dx. What does the calculator give me for the answer? 1.462651746. 1.462651746. That's what the calculator tells me what the integral is. Does that make sense? Now, last class, we did, turn back a couple of pages here, we actually did this problem where we were trying to approximate the integral from 0 to 1 of e to the x squared with n equals 4. So we're using 4 partitions here. And what do we get for the trapezoidal rule? It was what? 1.490678886. So here it is. I'm just going to go ahead and write that in there because we've already done that one. 1.490678886. See 2 pages ago of notes. Okay? Because what we're into this section is about error. All right, so part C here. Find the maximum error using the error bounds and compare it to the actual error. Let's first calculate the actual error. What is my actual error going to be? According to my rule, still written up here, the rule for actual error is the true integral. We're going to assume the calculator gave me the rule integral. 1.462651746, and then I'm going to subtract off the approximate answer, which was my T4, which was what? 0.490678886. What do I get when I do that? I'll put it on my calculator here. I'll take this number and subtract off 1.490678886, and I get a negative 0.02802711141. That is my actual error. Now, please tell me, what is that negative telling me? What's the negative telling me? Now remember, the formula for this actual error is the true integral minus the approximate, right? And I got a negative 0.028 answer. What's the negative telling me? The approximation is what? It's bigger. The reason why, the true integral minus the approximation, because you're subtracting off and you still got negative, that means the approximation is an overestimate. If I do true minus approximation and it's positive, that meant it was an underestimate. Does that make sense? So this is, and you can actually look at the numbers and see that this is actually an overestimate of the true interval. That's what the negatives tell me. But now, here's what we want to show you guys. We actually want to use the error-bound formula. Now, this is trapezoidal rule. So the error-bound formula for trapezoid, you notice that it's absolute value. So it's only going to give me the positive. It's not going to say it's an over or underestimate. It's just going to give me how much off this thing is. But that error is less than or equal to. So this is bounding the error. The formula is k times b minus a cubed over 12n squared. Okay? Well, remember, this is the problem that we're trying to use here. So clearly, a is equal to 0, b is equal to 1. We did t4, so n was equal to 4. So I'm going to plug that in. So that's going to be equal to k times b is 1 minus 0 cubed over 12 times n, which is 4 squared. So all I need to do to calculate this trapezoidal rule error is figure out what k is. By formula, k is the maximum value of the second derivative. What was my function here? My function was e to the x squared. I'm going to show you how to calculate k in this formula, okay? To calculate k for the trapezoid or midpoint rule, you got to do the second derivative. So, to get to the second derivative, you got to take the first derivative. Good practicing of calculus 1 skills. How do you take derivative of e to the x squared? What rule? Well, derivative of e to the x is e to the x, but this is calc 1 now. So what rule do I have to use to take derivative of e to the x squared? E to a function. It was called what? Chain rule. Derivative of e to a function is e to the function times derivative of the exponent. So that's going to be e to the x squared times 2x. Well, you can clean that up and it becomes 2x times e to the x squared. So now, what rule do I have to use to take the second derivative? 2x times e to the x squared. Product rule. Derivative of the first times the second plus the first times derivative of the second. Derivative of the first. Derivative of 2x is 2 times the second, e to the x squared, plus the first, 2x times derivative of the second. Well, derivative of e to the x squared chain rule is e to the x squared times 2x. So you can clean up this second derivative, and you get 2 e to the x, squared. 2 e to the x squared plus a 2x times a 2x is a 4x squared, e to the x squared. And I want to remind you, when you're doing this stuff, your k is the maximum value of the second derivative over your interval. What is my interval in this problem? What's a and b in this problem? 0, 1. So to find k, this is what you do. You graph it, and you only focus on the graph between 0 and 1. So I'm going to go over here to y equals, clear out my old function there, and I'm going to graph this guy. This is 2e to the x squared plus 4x squared times e to the x squared. Now watch what I do here. I type the function into y equals. I'm going to go to my window, and I'm going to change my window. Where's my window? We don't care about what's happening at 45. I don't care what happens at negative 102. Where am I looking at? Over the interval between 0 and 1. So I'm going to make x0, y1, sorry, x minimum 0, x maximum 1. And then to figure out what the y coordinates are, I'm going to do this. Now the T84, 83, and the 89 has it. It's called a zoom standard. Scroll down here on the T84, it's the zoom's 0. Zoom fit. You want to do a zoom fit on this particular guy. What it does is it sets the x values, you just did that, 0 to 1, and it fits the y coordinates so you can actually have a decent graph on this guy. And this is my picture. This is what 2e to the x squared plus 4x squared e to the x squared looks like. Now I'm going to change something slightly. I'm going to go back here and hit the window, and I look at my y coordinates. My y minimum was 2, my y maximum was 16.309. So I'm going to change that y minimum from 2 to make it negative 1 and graph it, because I want you to see where the x-axis is located at. It's actually at the bottom. So this is what my graph looks like. It's over here, and then it just continues to kind of blow up on me, like that. That's what my graph looks like. Now, listen to my words. K is the maximum value of the second derivative over this interval. Where is what I mean by maximum value is the farthest distance away from the x-axis. Which point between 0 and 1 of my second derivative is the farthest distance away from the x-axis? Where's it occurring at? At 1 right here. So what the farthest distance is this guy right here, and this is your k value. So to calculate what k is going to be, I want to evaluate where the farthest point is, which is at 1. So second, calculate value at x equals 1, and the distance or the y coordinate is 16.309. 16.309691. 16.309691. That is my K value. So, K being equal to 16.309691 times 1 minus 0 cubed over 12 times 4 squared. And I'm going to put that on my calculator, and I'm going to calculate the error bound for the trapezoidal rule. So second quit, clear it out, plugging this on the old calculator here. I'll put it up here so you guys can see this thing. All right, here we go. It is 16.309691 times 1 minus 0, yeah, I don't really need to do that, but I'm doing it for your benefit, cubed. Yeah, 1 minus 0 is 1, cubed still 1. Divided by, but this is the important part to be able to get this correct answer on the calculator. You've got to make sure you put parentheses around your denominator. Now, all the numerators being multiplied, so you're good to go there. But put parentheses around the denominator. What's my denominator? 180 times, parentheses there, parentheses 180 times 4 to the squared power, 4 squared, and then close parentheses. Parentheses around the denominator. What do I get for my error bound? I got 0.005663087
Are you using 12?
Oh, wait a minute, did I lose the 12? I am, sorry. Let's go back and redo that. You're right, it's supposed to be a 12 there. I don't know, the 180 is from the Simpsons Rule. My fault. Try that one. Does that look a little better? 0.084, 16.309691 times 1 minus 0 cubed divided by, make sure I did it right here, 12 times 4 squared, which is, like you said, 0.08. So let's get the right number here. 0.084963073. 4094. Does that make sense? 0.084946303. Now here's my question for you. That is my error bound for the trapezoidal rule. My question is this. Is this actual error within this? Now remember, the bounded error does not have a plus or minus on it because it's absolute value. So this number will always be positive because K is always positive. However, here's the deal. The actual error was 0.028, right? 0.028, negative 0.028. But in terms of how much off it is, just get rid of take the absolute value of that, it's 0.028. That's the actual error. This formula says that the error will be less than or equal to 0.084. Is 0.028 less than 0.084? Yes, it is. Now you go, well, geez, that's more accurate here. Yeah, but here's the deal. Let me explain why this is important. You see, to actually find the actual error, you actually have to know what the integral is. But to use the error bound formulas, it does this weird K times B minus A cubed over 12 or 24 n squared if it's the trapezoidal midpoint rule, and it's K times B minus A to the fifth over 180 into the fourth when it's Simpsons Rule. It doesn't actually use the integral. It uses some weird deal about the second derivative or the fourth derivative at best. Does that make sense? It doesn't use the integral. And so it does give me a less than or equal to bound on this thing, but the bound is accurate. Does that make sense? So it's not perfect, but it doesn't use the integral is my point. And now, look at this next question. You'll see the power of this. Now, most of my folks that take my class here in Calculus 2 are engineers. Now, don't get me wrong, we got math majors in here, I got computer science majors, I got chemistry, biology majors, but mostly I got is civil, mechanical, electrical, computers engineering, I got motorsports engineering, I got engineers all over the place in here. Raise your hand if you're an engineering major. Yep, that's what I thought. So 90% of my class is going to be engineers. That's normal. Now, what's the real deal about this stuff? Let me explain where your future is going to lie. And this is all majors that are science majors. You know, English majors, they may not care, but the rest of us do. Here's the deal. okay? You've got an integral out there that you need to find the actual integral to. This thing's nasty. You don't even know how to integrate it. Don't even know where to start on how to integrate this thing. But because there's no tables seem to help you out, all the tricks we ever showed you guys doesn't work, but I got to get a handle on this thing. And I have something called tolerance within my world. I got to get my answer within, 0.001 millimeters or something like that. I got some kind of a tolerance. As long as I can get this thing within, we can build it and maybe the part will fit. You understand what I'm talking about? So, look at this next question. What is the smallest value of n that will yield an error within 0.001? That's the question. Let me put it to you in reality. How many partitions do I need to take the trapezoidal rule out? Because there's problems with the trapezoidal rule. How many partitions do I need to take the trapezoidal rule out so I can get my tolerance within that 0.001? So I can get my calculations correct so I can go build what I need to build. Does that make sense? And the darn thing will fit. So, how many partitions do you need? Well, here we go. Remember, this was trapezoidal rule. Let's see if I can remember the form again. Trapezoidal rule is k times b minus a raised to the third power over 12n squared. That is the error-bound formula for trapezoidal rule. And that's got to be less than or equal to my tolerance, my error, 0.001. I want my error to be within 0.001. Now again, in this problem, we know that k was equal to 16.309691. See previous problem, that's where my k was. My a was equal to 0. My b was equal to 1. And the question is, how many n's do we really need to take out of this guy? I mean, look at it. We took 4, and my tolerance was, when I did 4 partitions, was less than or equal to 0.08. That's correct to pretty much 1 decimal place. Okay? The actual error is actually, it's a little above, but 1 decimal place is all you really got in this one because of the 0.0 something or other. Does that make sense? I want it to be accurate within 0.001. How many partitions do I need? So plug this information in. This gives you 16.309691 times 1 minus 0 cubed over 12n squared. Leave n as the variable and set it less than 0.001, and it becomes an algebra question. Solve for n. Now, how would you solve for n on this one? Well, first off, okay, I do the easy math. What is 1 minus 0 cubed? Okay, well, so 1 minus 0 is 1 cubed is still 1. So that part kind of just goes away there, right? So if I'm going to solve this thing, I've got a fraction less than or equal to its inequality, 0.001. First thing I want to do is, after I clean up the little arithmetic here, is get rid of my fractions. I'm going to multiply both sides by 12n squared. When I do, it cancels my denominator. That gives me 16.309691 is less or equal to 0.001 times 12 is 0.012. N squared. Give n squared there. Now, what you going to do to solve for n? Well, let's get that n squared by itself. What's your next move? I'm going to divide by 0.012 on both sides. So I'm going to show you, I'm literally doing this on the calculator here. So I'm going to take that 16.309691 divided by 0.012, and I get this. 1,359.140917 is less or equal to n squared. What's my move now? Solve for this sucker. I want to take the square root. Now, officially, when I take a square root problem, I can do plus or minus, but n stands for something or other. The number of partitions. You can't have negative partitions. We're counting these guys. So when you do take the square root, it is a positive square root. So I'm going to take the square root of this answer there, and what do I get? I got n has got to be greater than or equal to 36.86652,841. But here's the problem. I want to know the number of partitions I need to take this thing out to. I cannot have a 0.86652,841 of a partition here. So what am I going to do? I don't care what the decimal is. This is not decimal rules. We're trying to count partitions. So if you've got any decimal at all, what do you always do? Round it up. So when we round up, what is my n going to be equal to? How many partitions do I need? 37. Does that make sense? Which means if I go back and do this trapezoidal rule with n equals 37 partitions, I would get my tolerance for my integral within that 0.001 answer. Does that make sense? You see the purpose of this stuff. Well, let's do another one. All right, this one's kind of special. I'm giving you the function f of x equals the natural log of x. First thing I want you to do is I want you to actually find the integral from 1 to 4 of the natural log of x dx. I want you to integrate this guy. This is integrable. See last test. I want you to integrate this thing. Now, what technique will I use? So if I want to integrate this guy, so I'll write it up here, the integral from 1 to 4 of the natural log of x dx, U substitution doesn't work. Well, first off, I don't know this rule. I don't have it memorized. I know that the derivative of the natural log of x is 1 over x, but I don't know what the integral of the natural log of x is. So, and it's not a rule I have memorized. U substitution doesn't work, but you can view it as a product because I can do it times 1. So when I integrate natural log of x, see last test again, what technique do I traditionally use? Integration by parts. So, coming back to Honchi again, integral of u dv equals uv minus the integral of v du. So in this particular problem, you got to let du equal to part of it and dv is the other part. What are you going to let u equal to when you're trying to integrate a natural log of x times somebody? It's part of that Lytle principle that you're supposed to have memorized from section 6.1. What do you let u equal to when you're trying to integrate a natural log function times somebody else? You always let u equal to the natural log of x. That makes du completely change. What's the derivative of natural log of x? 1 over x dx. And it makes dv equal to 1 dx, which makes v equal to, integrating 1, you get x. So I plug it into my function here, which will be u times v. That'll be x natural log of x minus the integral of v, which is x times du, which is 1 over x dx. And it's literal substitution. But if you remember anything about integration by parts is this. After you plug it into the formula, integral u dv equals uv minus integral v du, you clean up the second integral before you integrate it. So, what is x times 1 over x? Cancels to be 1, so this is x, natural log of x minus the integral of 1 dx. This is equal to x, natural log of x minus, what's the integral of 1? X. But no plus c's on this thing because we have original bounds from 1 to 4. According to the fundamental theorem, you plug in top minus plug in bottom. So this would be 4 natural log of 4 minus 4 minus 1 natural log of 1 minus 1. Well, from the, 10th grade or whatever, we know that the natural log of 1 is equal to what? 0. So I end up getting, this is equal to 4 natural log of 4 minus 4. A minus makes it plus 1. So my actual answer is 4 natural log of 4 minus 3. That is actually the exact integral, exact value. Does that make sense? Good practice. But, okay, so that was part A. So my answer for part A is this. It is 4 natural log of 4 minus 3. Second part is this. I want you to use Simpsons Rule to find S6 for this particular integral. S6, that's telling you how many partitions you got. 6 partitions. Again, your A, because we're integrating from 1 to 4, A is equal to 1, B is equal to 4. That's going to imply that your delta X is equal to B minus A over N, which is 4 minus 1 over 6, which is equal to 1/2. And I'm just going to separate this stuff right here. from what we've done before, so there we go. All right. Now, I'm going to put my partitions out here. We're starting with A, which is 1. What is my delta x in this problem? My delta x is 1/2. So 1 plus a half is 3/2. Another half makes it 2. Another half makes it 2.5 or 5/2. Another 2 makes it 3. Another half makes it 3.5 or 7/2. And another 2 makes it 4. And this is where I stop at. How many partitions were I supposed to have? 6. Count them off. 1, 2, 3, 4, 5, 6. Now, this is the work we expect to see on a Simpsons Rule problem. So I've got my data here. My original function that we're trying to integrate is the natural log of x. And so I'm going to write down my formula. For S6, the formula is, what is the Simpsons Rule formula? It is delta x divided by what? You got it memorized yet? 3 times f of a plus 4 times f of x1 plus 2 times f of x2 plus plus 4 times f of xn minus 1 plus f of b. That is Simpsons Rule. Always write down the rule. That's worth partial credit on a Simpsons Rule problem. You at least know the rules. If you can't plug in the numbers, at least you know what you're supposed to do. Now plug in what you know here. So to calculate S6, your delta x is going to be 1/2 divided by 3 times f of your first point, which was 1, plus 4 times your first partition point, internal partition, which is 3/2, plus 2 times f of 2, plus 4 times f of 5/2, plus 2 times f of 3, plus 4 times f of 7/2, plus your end partition, just f of b, f of 4. But what was your function? What are we trying to integrate? The natural log of x. That was my function, f of x, because remember the original problem was we're supposed to integrate right here, the integral from 1 to 4, natural log of x dx. Natural log of x is f of x, a is 1, b is 4, that's where I'm getting this information from. So, to show my work, S6 would be equal to 1/2 divided by 3 is a 1/6 times the natural log of 1 plus 4 times the natural log of 3/2 plus 2 times the natural log of 2 plus 4 times the natural log of 5/2 plus 2 times the natural log of 3 plus 4 times the natural log of 7/2 plus the natural log of 4. So to actually calculate S6, at this point, it becomes a calculator problem. Does that make sense? So, here we go. Right here is where most people are going to mess this problem up. The inability to actually plug stuff into their calculator correctly. One false move, parentheses in the wrong spot, whatever, you're going to mess this thing up. So I'm going to show you something wrong. So I'm going to first put it on the calculator, parentheses, 1/6 times another parentheses, and here we go. It's the natural log of 1 plus 4 times the natural log of 3/2 plus 2 times the natural log of 2 plus 4 times the natural log of 5/2 plus 2 times the natural log of 3 plus 4 times the natural log of 7/2 and then plus the natural log of 4. And then close parentheses for the natural log and close parentheses for the fact that there was a whole thing being multiplied by a 6 out front. And according to my calculator, I got the answer 2.544648089. That's what I got for Simpsons Rule. But I happen to have on my calculator the program. Let me show you how the program works. Why you really want this program. Here we go. First thing, go to y equals. Clear off any kind of function you got in your calculator, and under y1, type in the function that you want to actually get the Riemann sum for. What was it? It was the natural log of x function. You with me? You don't have to graph or anything, you just enter, just type it in and hit enter so it's in the memory of the calculator. So So now, second quick, go to the home screen. These are the programs I have on my calculator. Your goal is to get this program on your calculator. At the bottom of the programs, you'll see that I have a program called Riemann. Okay? I'm going to hit enter beside the Riemann program. Again, this is the T84. 89 works slightly different. And now I hit enter and it initiates the program. What was my A value on this problem? What was A? 1. What was B? 4. Now here it comes. What is N? Now remember, in this problem, N is 6. But the way the programming works, it's a short program. And it's a short program because I told you guys before that the Simpsons rule was derived from that you take 1/3 the trapezoidal rule plus 2/3 the midpoint rule, and it gives you Simpsons rule for twice the ends. So we're programming the midpoint and the trapezoidal rule for you, and we're using that little fine trick to be able to manipulate those two answers to get the Simpsons rule, but it gives you for twice n. So the program is going to give me a twice n for Simpsons rule. So if I wanted 6 partitions, what n do I need to plug into knowing that the program is going to double that n for Simpsons rule? 3. So if I type in n is 3, the program doubles the n value for Simpsons rule. So I'm going to hit enter, and what does my calculator give me? It gives me L, left Riemann sum. It gives me R, right Riemann sum, T, trapezoid, midpoint, and S, and look at parentheses, which I want to remind you, 2n. Since n was 3, this is the Simpsons rule for 2 times 3, which is 6. And what answer do I get? 2.5446488. The only thing that's missing is the 9 at the end because we just cut off the last decimal. It's really sweet. Because where most students are going to screw this problem up is they'll do this. They'll write down the formula. They'll write down the numbers as supposed to plug it in. They'll even write down the plug in the numbers into the function, which you're supposed to write down. This shows your work. This doesn't show squat on terms of work, but it shows me what the right answer is. Does that make sense? This is a way of checking your answer because, like I said, when you type this in on your calculator, it's real easy to screw up by putting a square inside the parentheses instead of outside the parentheses where it belongs. One false move, you blew the whole problem. Does that make sense? The program's designed to help you guys out. So it's very advantageous, and I'm going to allow you guys to have it on my test, but this is the work I want to see. But it's also very advantageous on that final exam. Because, again, this is the kind of problem they'll put on the final exam. They're grading this, but at the end of the day, they want to see what the final answer is. And you want to make sure you want to have comfort here. Double check it on your calculator. But you got to show your work. Let me tell you, even on the final exam, you got a problem like this, and they got no work, but yet there's a wonderful answer sitting there waiting for you. They take off extra points for crap like that. Show your work, okay? Now, continue on. Find the maximum error using error balance and compare it to the actual error. All right. So, first off, let's calculate that actual error. Actual error, again by formula, is the true integral minus the approximation. Now in this problem, we did do the true integral. It was 4 natural log of 4 minus 3. And then I got to subtract off my approximation, which is 2.544648089. And let's see what we got when I do that. So I'm just going to hit clear and enter and get done with that. And now I'm going to type this thing in. Parentheses, 4 natural log of 4 minus 3 minus 2.544648089, and I got an error of, what did I get for an error? I got 5.2935544796 E negative 4. What is this E negative 4 telling me? Scientific notation, times 10 to the negative 4th. So what is my actual error? I'll move the decimal place 4 places to the left. I get 0.0052935544796. That is my actual error. This thing is actually accurate to 3 decimal places is what it's telling me. Does that make sense? But I actually knew what the real answer was. Now let's compare it to the error bound. But remember, this is the error bound for Simpsons rule. The error bound for Simpsons rule is less or equal to k times b minus a to the 5th divided by 180 into the 4th. Pure memorization. But wait, it gets worse. in this problem, A was equal to what? What was A? What was my lower bound? 1. What was B equal to? 4. And N was equal to 6. So this would be equal to K times 4 minus 1 to the 5th over 180 times 6 to the 4th power. Does that make sense? Questions? I got to find what K is. How do I find what K is? For Simpsons, K is equal to the absolute value of the 4th derivative, right? Over the interval between A and B. So I got to find the 4th derivative. What's my function again? What was my function that we were trying to integrate? Natural log of x. Here we go. What's the first derivative? Let's derive natural log of x. 1 over x, but that's also the same thing as x to the negative 1. What is the second derivative? Negative 1 x to negative 2. What's my third derivative? Calculus 1 comes back and haunts you again. That'll be 2x to the negative 3. And that's the third derivative. What is the actual fourth derivative? Negative 6 x to negative 4. Better yet, negative 6 over x to the 4th. There is my fourth derivative. I want to find the maximum error, maximum bound of this guy over the interval. What is my interval in this problem? Between what? 1 and 4. So what am I going to do here? I'm going to go to y equal, clear it off, and type in the function negative 6 divided by x to the 4th. And I'm going to hit my window, and my window now is going to be between 1 and 4. Does that make sense? And I'm going to hit that zoom 0 button on the T89. Zoom 0, and let the calculator figure it out. It's between 1 and 4. And there's my graph right there, but I'm going to change the window because I want to see where the x-axis is. And the y's are between negative 6 and negative 0.02. So I'm going to make that negative, positive 1 so I can see it. I'll make that, delete that, positive 1. And I graph it, and so my graph looks like this. Does that make sense? Where is the maximum value? Again, I repeat, to understand maximum value is the furthest distance away from the x-axis. Where is the point that has the furthest distance away from the x-axis? Is it at 1, is it at 4, or is it in the middle somewhere? The furthest distance is at 1. This is my farthest distance. So when I find this particular value, I'll go second, calculate, it occurs at 1, value at 1, once I understand my graph. And what do I get? I got the value down here is at the point 1, negative 6. So what is k equal to? Remember, k is the maximum of the absolute value of the fourth derivative. With me? So what is k equal to in this problem? So my maximum value is negative 6, but you got to take the absolute value of that guy. K has always got to be positive. So what's k equal to? 6. So plug it into the formula. This will be 6 times 4 minus 1 to the 5th over 180 times 6 to the 4th. And let's see what we get for the error. And again, plug it on my calculator here. I get 6 times 4 minus 1 to the 5th divided by parentheses around the denominator. 180 times 6 raised to the 4th power. Close parentheses around the denominator. And what do I get? 0.00625. So this tells me by the error-bound formula that the Simpsons rule is going to be for 6 partitions on this function of the natural log of x is 0.00625. Does that make sense? But now, compare it to the actual error. Is the actual error 0.0005, 0.0005, is that within the interval of less than 0.00625? Yes, it is. But this did not use the actual integration. The actual error does. There's the difference. Take a look at the next question here. What is the smallest value of n that will yield an error within 0.0001. In other words, I set my tolerance at 0.0001. I want to use the Simpsons rule to do this particular problem. What is the number of partitions I need to take this thing out to assure my answer is going to be correct to within 3 decimal places? So, again, my Simpsons rule error is less than or equal to k times b minus a to the 5th over 180 into the 4th, because we love memorizing stuff, and that's just the one of the things we got to know, which is equal to, what was k in this problem? 6. B was 4 minus a was 1 raised to the 5th divided by 180. Remember, the question is, what is in? Leave it blank, leave it a variable, into the 4th, and you're going to set that less than or equal to 0.0001. And you're going to solve for n. If I was going to do this problem, this is how I would do it. I'm going to solve for n, so I'm going to take this and multiply both sides by n to the 4th. I'm going to get that n to the 4th by himself. What that's going to give you is this. 6 times 4 minus 1 to the 5th over 180 is less than or equal to 0.0001 times n to the 4th. Now this is nothing but a number. Let's go figure out what that number is. 6 times 4 minus 1 to the 5th. Sorry, it's not up to Gus to see it. To the 5th over error divided by 180. I got 8.1. Did you guys get that? So I've got 8.1 is less than or equal to 0.0001 into the 4th. Now, what am I going to do to solve for n to the 4th? What's my next algebra move? Because this is nothing but arithmetic here. I'm going to divide by 0.0001 on both sides. When I do that, divided by 0.0001, I end up getting 81,000 is less than or equal to n to the 4th. Now, mathematically, what do I got to do to get rid of that 4th power so I can solve for n? Take the 4th root of both sides, that's fine. But where's that 4th root button located on the calculator? Well, it's got one, but I'm not going to look for it. Because remember, when I want the 4th root, that's the same thing as raising it to the what? 1/4 power. Remember, a radical is a fractional power. So I'm going to raise that 81,000 to the 1/4 power, and I end up getting this. N has got to be greater than or equal to 16.87023976. Does that make sense? However, as mentioned to you guys in that last problem, here's the deal. I can't have a 0.8702396 of a partition. So what are you always going to do with these answers? Round them up. So what is the answer to my problem? That is wrong. Hugely wrong. Why? You're right. You rounded up, and I'm not going to argue the fact you rounded up at 17, but you forgot what game you're playing. This is Simpsons Rule. What does n have to be Simpsons Rule? It's a trick question, but it's the right answer versus the wrong answer. So you're right. You've got to round up, but because it is Simpsons Rule, you got to make sure that you round up to get the next even integer. So when I round up from 16.807, I don't care what the decimal is, round it up, I get 17. 17 is not allowed on Simpsons Rule because it's got to be even. So you keep rounding them up. So what is the actual answer? Answer is 18. That's how many partitions I got to have for Simpsons Rule for this problem. Does that make sense? Don't forget what. Trapezoid and midpoint rule, you don't care. Even or odd, don't care. But Simpsons Rule has to be even. Don't forget to keep that in the back of your mind. Well, let's do a web work problem before we move on into section 6.6. A student is speeding down Highway 16 in her fancy red Porsche when her radar system warns her of an obstacle 400 feet ahead. She immediately applies the brakes and starts to slow down and spots a skunk in the road directly ahead of her. The black box in the Porsche records the car's speeds every 2 seconds, producing the following table. 0, 2, 4, 6, 8, 10, and 95, 85, 45, 25, 15, and 0. So this is measured in seconds. This is measured in feet per second. All right. The speed decreases throughout the 10 seconds it takes to stop, although not necessarily at a uniform rate. A, what is the best estimate of the total distance the student's cars travel before coming to rest? Note the best estimate is not probably the over or under estimate that you mostly easily find. Use the trapezoid approximation. Why do we have to use the trapezoid approximation for the best estimate? All right, first off, you know the left and right Riemann sums give you over and under estimates. So anytime they ask you for over and under estimates, you're going to use the left and right Riemann sum. So what's your best Riemann sum? It's the Simpsons Rule. But how many partitions you got to have do a Simpsons Rule? Even. These are your partitions. From 0 to 2, 2 to 4, 4 to 6, 6 to 8, 8 to 10. That's 1, 2, 3, 4, 5 partitions. That's odd. That's why you can't use Simpsons Rule. Well, then the next best one would be midpoint. The problem is, on your partitions, you don't have midpoint data. Between 0 and 2, the midpoint is 1, and I don't have any information about what's going on at 1. So I can't use the midpoint because I don't have midpoint information. So as you go from your hierarchy, what's the next best thing in line? Trapezoid. That's why the trapezoid rule is appropriate here. So let's do the trapezoid rule. So to do the trapezoid rule, I'll write it down here. So how many partitions do I have here? I got 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. There we go. So I got 5 partitions. So this is going to be a T5er. What is my delta X in this problem? What is my change within my widths? It's 2. I want to remind you, what is the formula for trapezoidal rule? It is delta X divided by 2 times f of A plus 2 times f of x1 plus 2 times f of x2 plus plus 2 times f of xn minus 1 plus f of b. In English, it is delta X divided by 2 times f of A plus 2 times all the internal functional values plus f of b. Okay? Your delta X is equal to 2 divided by 2. F of your first point at 0 is 95 plus 2 times your first internal point is at 2, which is at 80, functional value is 85, plus 2 times 45 plus 2 times 25 plus 2 times 15 plus f of b, your endpoint's at 10 seconds, which is your value is at 0. Well, 2 divided by 2, I can do that kind of math. That's 1. So that'll be 95 plus 2 times 85 plus 2 times 45 plus 2 times 25 plus 2 times 15 plus 0. And what do I get? 435. What is that telling me? According to the trapezoidal rule, she traveled 435 feet. Let's remind ourselves of this accident that's about to occur. How far away, according to the onboard radar system, our Porsche seems to have, how far ahead was this skunk in the road? 400 feet. So according to the trapezoidal rule, what? She hit the skunk and dragged him another 35 feet. Messy problem. Okay, so continue on. Well, given the fact that the Porsche slows down during braking in a sharp, is very sharp here in terms of the braking system here, calculate the under and over estimate of the distance traveled. Remember, anytime you hear the words calculate from a Riemann sum perspective, over or under estimates, that's your left or right Riemann sum. Which one's which? I don't know until we do it. So just do the left Riemann sum and the right Riemann sum. Okay? The left Riemann sum formula is delta X times, use left points, f of A plus f of x1 plus f of x2 plus plus f of xn minus 1, the point on the left. And the right Riemann sum is delta X times f of x1, the point on the right, plus f of x2 plus f of x3 plus plus f of b. B will be on the right. Just to remind you of the formulas. So, using my chart up here, my delta X is equal to 2 times f of A was 0, would be 95, plus your next one would be 85, plus your next one is 45, plus the next one is 25, plus 15. I want to show you where these numbers are coming from. This is your partition from 0 to 2. The point, left Riemann sum point on the left. 0 is on the left is 95. From 2 to 4, the point on the left is 85. From 4 to 6, the point on the left is 45. From 6 to 8, the point on the left is 25. From 8 to 10, the point on the left is 15. That's why I stopped at 15. So I end up getting, when I calculate this thing out, put it up here, you guys can see this. This is going to be 2 times 95 plus 85 plus 45 plus 25 plus 15. I end up getting 530 feet. Okay? And for the right Riemann sum, it's going to be 2 delta x times. Now on the points on the right, start at 85 plus, again, the point on the right, the next one would be 45 plus 25 plus 15 plus 0. With your partitions, use the points on the right, 85, 45, 50, 25, 15, and 0. So when I add these guys up, I end up getting 340 feet. Just did on my calculator. So again, not knowing which one's which, but now knowing my numbers, I know. What was the underestimate? The underestimate was 340 feet. So according to the right Riemann sum, she missed the skunk and still had another 60 feet to spare, right? But according to the left Riemann sum, which is my overestimate, 530 feet, she not only hit the skunk, she dragged him an extra 130 feet after this thing grinding him into the, no doubt, the grill of the car or whatever. So no doubt smells good. So look at your next question. Which of the following statements can you justify from the information? A, the black box data was inconclusive. The skunk may or may not have been hit. B, the skunk was hit by the car. Or C, the car stopped before hitting the skunk. Which one is it? Well, the answer is A. Let me explain why the answer is A. Now, according to the trapezoidal rule, we hit the skunk. According to the overestimate, we hit the skunk and drug him a long way. However, because of that right Riemann sum, it's still possible, because of the curvature of this thing, we could have missed the skunk because the right Riemann sum did miss the skunk. So as long as one of my answers misses the skunk, the answer is A, the data is inconclusive. However, this is web work and everybody's got one in here. If your answer was more than 400, and this one was more than 400, and your underestimate was more than 400, then you could definitely say B, you hit the skunk. Or if your trapezoid was under 400, the overestimate was under 400, and the underestimate was under 400, you could definitely say C, you missed the skunk. But because one of the pieces of data didn't allow me to hit the skunk, but the other ones did, it's quote-unquote inconclusive. Does that make sense? All right. Last 5 minutes in class, let's go on to the last section. Section 6.6. Section 6.6 is on improper integrals. Improper integrals. Now, hopefully you watched the awesome pre-section video some idiot made for you guys, but let me explain in a nutshell what an improper integral is. We're talking about integral with bounds. Now, there's 2 different types of improper integrals. If you look at this first one that was done on the pre-section video here to kind of introduce this section, you were talking about integrating things with bounds. Well, look at this first one. I'm integrating from 3 to infinity for 5 over x dx. Well, there's your problem right there. You got an infinity on the bound. Infinity is an idea. It's not a number. It's the biggest number you can think of plus 1. You never get there. And because this is not a number, we call that an improper integral. That's what I call type 1 improper integrals. They're real obvious to see. They got an infinity on the bound. However, you turn the page over on the other pre-section video problems that I did. Let's look at this problem down here. This is a good problem here. Look at this problem. The integral from 3 to 10 of 7 over x minus 5 dx. Well, this thing looks fine. But you notice one thing. Look at the function, 7 over x minus 5. You happen to have a point that does not exist on this thing. There's a vertical asymptote or a point that doesn't exist. What value of x does not exist with the function 7 over x minus 5? 5, because you're not allowed to divide by 0. And also happen to notice this. Your bounds are between 3 and 10, and 5 is somewhere in the middle of your bounds. You're trying to integrate over points that don't exist. That's improper. That's not allowed. You can't integrate over things that don't exist. So this is what we call an improper integral, what I call a type 2 improper integral. They're harder to find. You've got to train yourself to remind yourself to look at the functions and the points that don't exist and compare it to the bounds. And if it's within the bounds, it's improper integral. If it's outside the bounds, it's a regular integral. Proper, if you will. Does that make sense? So, again, please watch the pre-section videos on this stuff, but what's going to happen here is for us to be able to calculate an improper integral, we're going to go back to our standby of doing things as we approach numbers and stuff, and that's called limits. So let's remind ourselves of a few limit properties here. This first one right here. When I take the limit as x approaches infinity of 1 over x, or when I take the limit as x approaches infinity of a constant over x, arbitrary constant here. When the denominator gets bigger, what does my fraction going to go to every time? 0. So, when you got the infinity on the bottom, infinity in the denominator, the fraction goes to 0. Classic limit law. Some other ones. When I take the limit as x approaches 0 on the plus side of the natural log of x, I get negative infinity. If you look at the graph of that, as you approach the x-axis, the natural log of x drops straight down. So things you need to remind yourself. The natural log of 0 is equal to negative infinity. The limit as x approaches infinity v dx is infinity. In other words, e to the infinity is actually equal to infinity. Let's jump over here real quick. When I take the limit as x approaches infinity of 1 over x to any power, as long as the power is officially greater than 0, and that'd be greater than 1, greater than 0, 1 over infinity to a positive power, that infinity is in the denominator, which means it goes to 0. So 1 over infinity is always equal to 0. The next one, limit as x approaches infinity, the natural log of x is equal to infinity. In English, the natural log of infinity is infinity. That's what you got to remember. Natural log of 0 on the plus side is negative infinity. Natural log of infinity is infinity. The next one, the limit as x approaches infinity of e to the negative x is equal to 0. In other words, e to the negative infinity is actually equal to 0. And again, these are reminders from stuff we did in Calculus 1. So this was kind of reminding you of these properties here. And the last two are these. The arc tangent of infinity actually gives you pi halves, and the arc tangent or tangent inverse of negative infinity gives you negative pi halves. Little property of arc tangents there. Go back, Calculus 1, look at the graphs. Now, you're going to see these guys are going to be very helpful when you start to analyze these things, but let me explain what's going on here. Consider the function, so here's a visual perspective. Consider the function f of x equals 1 over x. Okay? And we want to integrate from 0 to 2 of 1 over x dx. We want to figure out what the integral is. The problem is, again, remind yourself from chapter 5.1 and 5.2 and 5.3, when you integrate, you're calculating the area under the curve. So here's the function, y equals 1 over x. There's my curve. And we're looking at the bounds between 0 and 2. Well, here's 0 and here's 2, so we're talking about this area. The problem is very simply this. You see that function 1 over x? There's a point that doesn't exist on that function. What point does not exist on the function f of x equals 1 over x? 0, because I can't divide by 0. And you'll notice 0 is a vertical asymptote. As I get very close to 0, the graph blows up. In terms of area, I seem to be getting more and more area. So as I get closer, is this area going to, here's the question, is the area going to get pinched off and I'm actually going to get an actual value of area, or is I'm going to continue to add more and more area as I go up the chain of command here? That's the question. So this is how we calculated it. So we're going to calculate the integral from 0 to 2 of 1 over x dx. Your problem is the 0 point because it does not exist for the function 1 over x. So how you turn an improper integral to a proper integral is you use limits. So this would be equal to, pick out your limit, take the limit, pick out your favorite letter, I like A's, Take the limit as a approaches 0, but you're integrating it from 0 up to 2. 0 up to 2. So you're on the positive side of 0. So you can't quite plug in the number, so you can do a limit as you approach that number. Take the limit as a, takes the limit as a approaches 0 from the plus side of the integral from a to 2 of 1 over x dx. This turned an improper integral to proper, so it's now about notation, aka show your work. So this is going to be equal to the limit as a approaches 0 on the plus side of, what's the integral of 1 over x? We know that one. What's that? Natural log officially absolute value of x evaluated from a to 2. According to the fundamental theorem of calculus, you plug in top minus plug in bottom. So you keep writing this limit as a approaches, in this case 0 on the plus side, of plug in top, this would be the natural log of 2, minus plug in bottom, the natural log of a. Now you got your answer, the problem is it has a limit to it. Now we're going to use calculus 1 limits. So first rule of limits is plug in a number. So this is going to be equal to the natural log of 2 minus the natural log of a, but a is going to 0 on the plus side. So this is the natural log of 2 minus the natural log of 0 on the plus side. This is proper. This is what it's equal to. Notice when I plug in my number, I don't write limit anymore. But what is that equal to? This is the natural log of 2 minus, and again, this is one of my limit properties. What was that natural log of 0 on the plus side equal to? Negative infinity. Now, clean up your answer. This is natural log of 2 minus negative infinity. A minus is a plus. Natural log of 2, some crappy 0.69 number on the calculator. Natural log of 2 is nothing but a digit, 0.69314,71806. But that'll be plus infinity. What's a decimal plus infinity? The answer is infinity. But because it's improper, we don't just write down infinity as answer. We're going to have to describe this. In other words, what's happening here is we are getting more and more area being added onto this thing. So there's an infinite amount of area, and when we have that infinity answer, we call that divergent. If you got a numerical value out of this thing, we would call it convergent, and we put the answer saying converges to 3. Does that make sense? But this one goes to infinity, so it's divergent. So next time, we're going to go back and start looking at a bunch of different kind of problems and start analyzing these guys. And remember to go back and practice your limit laws. And then don't forget, next Wednesday you got the calculator project due, and next Friday, homework number 3, test review 2 is due. See you guys then.